We're going to work through problem 4.46 from chapter 4 of Taylor's Classical Mechanics. This is a problem on the energy of interaction of two particles. This is an elastic collision of two particles. As in example 4.8, it's citing here where m1 has an initial velocity and it's going to interact with mass 2. And we're going to show that the angle theta between the two outgoing velocities satisfies theta is less than pi over 2 if mass 1 is greater than mass 2, but theta is greater than pi over 2 if mass 1 is less than mass 2. So what that's going to look like is we're going to have a mass 1 that's moving with an initial velocity, and we have a mass 2 over here, and once it interacts with mass 2, we're going to have a final velocity of both of these. And v2 prime. And we want to find, okay, what's this angle between them? So, we know that our kinetic energy is going to be conserved. So we can make a formula using the kinetic energy. We also know that mass 1 is not equal to mass 2. So our kinetic energy is going to be m1, that initial velocity, squared, is equal to, we can just write that as magnitude squared, is going to be equal to m1 v1 prime squared plus m2 v2 prime squared. So that's our kinetic energy. Kinetic energy is conserved. Now we want to go ahead and also use the property of momentum. Our momentum is going to be conserved. So using the property of momentum, we will have our m1 v1 is equal to m1 v1 prime plus m2 v2 prime. That comes from the fact that mv is our momentum is going to be conserved in the end. Now what we can do with this whole expression is go ahead and square both sides. So go ahead and square both sides. We'll end up with m1 squared v1 squared equals m1 squared v1 prime squared plus m2 squared v2 prime squared plus 2m1 m2. And then because these are vectors that we're going to multiply, if you were to FOIL this out or whatever method you have for squaring this binomial, we're going to end up with v1 prime dot v2 prime. So we have some similarities here. Now using that formula we gained from using momentum, we created a new formula here. We notice that if we take our kinetic energy, which is m1 v1 squared equals m1 v1 prime squared plus m2 v2 prime squared, we can take this, multiply both sides by m1, do the same over here by m1, and have m1 squared v1 squared equals m1 squared v1 prime squared plus m1 m2 v2 prime squared. Now we can go ahead and subtract that from this equation. So minus this whole thing from that equation that we gained from momentum, our kinetic energy multiplied by m1 on both sides. Make sure you do it to both sides. Now subtracting, we're going to have m1 squared v1 squared minus m1 squared v1 squared on the left hand side. Now we're going to have m1 squared v1 prime squared plus m2 squared v2 prime squared plus 2m1 m2 v1 prime dot v2 prime Subtract off these, minus m1 squared v1 prime squared minus m1 m2 v2 prime squared. You notice these are going to go away on the right hand side. These are going to go to 0. So you have 0 equals m2 squared v2 prime squared. I'm just going to reorganize our order here to make it a little easier to see what we're going to do next. Plus 2m1 m2 v1 prime dot v2 prime. With no mistakes, that should be what we get. Now, you notice we have a common factor here, which is m2 v2 prime squared times m2 minus m1 plus 2m1 m2 v1 prime dot v2 prime equals 0. Now, because we have it set equal to 0, assuming obviously that our mass 2 is not equal to 0, we wouldn't have a 0 mass there, we can divide by mass 2, get rid of it. Now, shifting things around, we're going to have negative m2 minus m1 v2 prime squared over 2m1 is equal to v1 prime dot v2 prime. Now we can get rid of that negative and just shift it into these over 2m1 all times v2 prime squared equals v1 prime dot v2 prime. Now, we know that our cosine, this becomes important here in a second because we're dealing with theta. We're trying to find the angle between these two. So we know that our dot product of these two vectors is the magnitude of each, right? The magnitude of each multiplied together times cosine theta. These are going to be positive, so they're not going to affect our actual value of our cosine theta. But this right here, if we can see what they're asking us up here, the qualifications, m1 greater than m2, theta must be less than pi over 2. So let's write that down. So if m1 greater than m2, theta must be less than pi over 2. So when theta is less than pi over 2, that means we're dealing with something in this area. So something in this region right here. Cosine is going to be positive. For this to be positive, mass 1 must be greater than mass 2, which that is confirmed by our formula here. Because you can see this isn't going to play a role, that's always going to be positive. This is always going to be positive. Only thing that matters is which one is greater. So that is confirmed, which is what they wanted us to show. And if m2 is greater than m1, our cosine is going to be equals a negative, right? Our cosine theta is going to be negative, which means that we must be falling somewhere on this side, as that cosine deals with the x values, which are negative on that side. So our theta must be greater than pi over 2. So if mass 2, going back up here to our drawing, if mass 2 is greater than mass 1, our theta is going to be greater than pi over 2. So if m2 is greater than mass 1, we're going to have a collision that looks something like this, right? We're going to have it going over here. It's going to hit on mass 2. Mass 2 is going to travel that way, and we could have mass 1 traveling this way. Right? Mass 2, this is the angle, is going to be greater than pi over 2. So that's when m2 is greater than m1. Now you can have m1 greater than m2 you have M1, just drawing it bigger to show that it's greater. It's going to collide with mass 2, and the angle between these, theta, is going to be less than pi over 2. That's what we're representing. That's what the question asked us to confirm, and we have gone ahead and shown all of that.